Welcome aboard the Relativity Express, and thank you for choosing relativity. Today we'll be traveling to an alternate universe in which the speed of light is different than in our own universe. We'll be making experimental measurements in order to attempt to determine what the speed of light is. Inside the train, represented here, will be an observer with a stopwatch. Outside the train will be an observer here with a stopwatch. The train for this first series of experiments will not be moving. A laser beam will be fired from the level of the floor up to a mirror affixed to the ceiling and back down. Each observer, the one in the train and the one outside the train, will measure the time it takes for light to travel the total distance of 8 meters, 4 meters up and 4 meters back. And the results are in. After numerous measurements to ensure accuracy, the person in the train finds the time is 8 seconds. The person outside the train observes the time to be also 8 seconds. Since the distance the light traveled was 8 meters in 8 seconds, both agree that the speed of light is 1 meter per second. Now a new series of experiments will be made in which the train will be moving forward to the right at a speed of 0.6 meters per second. When this measurement is made inside the train, it is again measured as 8 seconds. However, to the observer outside the train, the time is 10 seconds. The same event is observed to take a different amount of time. One way of explaining this is that rather than time being constant, the speed of light is constant. In other words, time varies, but not the speed of light. This can be graphically represented by these two triangles that you see here. The train travels 10 seconds at a speed of 0.6 meters per second. Therefore, it travels a distance of 6 meters to the right. The light goes along with the train, and the light also travels up and back by 4 meters. As a result, the total distance that light travels can be found to be 10 meters. This is the hypotenuse of a right triangle with sides 3 and 4. According to the Pythagorean theorem, this is 5 meters, and then this will be 5 meters. So the speed of light, according to the observer outside the train, will be 10 meters divided by 10 seconds, or 1 meter per second. And the speed of light, according to the person inside the train, will be 8 meters divided by 8 seconds for 1 meter per second as well. All of this can be described in an equation which is in all college level physics books under relativity. In this equation, delta T naught is called the proper time. That's the time when measured from a person, an observer that is, who is not moving relative to this experimental setup. The person inside the train with a stopwatch is not moving relative to the laser and the mirror. However, in the second series of experiments, the person outside the train is, and the time that that person experiences the event to take is delta T. This is called the relativistic or dilated time, and it will always be larger than the proper time. V squared is the velocity of the train, and c squared, or I should say v is the velocity of the train, and c is the speed of light. Now, when the velocity of the train is small compared to the speed of light, then this number becomes 0, and the square root of 1 is 1, and that means that the proper time and the dilated time will be approximately equal. Now let's take a look at how you could plug into this equation to calculate the dilated time. Okay, let's go about solving for the dilated time, delta t, by plugging into this equation. You won't need a calculator to do the math. It's very straightforward. The proper time is 8 seconds, and the speed of the train is 0.6 c. Remember, the train was moving at 0.6 meters per second, and the speed of light was 1 meter per second. Therefore, the speed of the train in terms of c is 0.6 c. When we square this, the c's cancel because c squared over c squared is 1. And just like when you take 6 times 6 and get 36, when you multiply 0.6 by itself, you end up getting 0.36. Then if we subtract 0.36 from 1, we get 0.64. And just like the square root of 64 is 8, the square root of 0.64 is 0.8. And then by dividing 0.8 into 8, we get our final answer. Delta t is equal to 10 seconds. Well, I'd like to thank you on behalf of myself and staff for choosing Relativity. We'll be arriving in your universe soon. The year on Earth is 2432, and if you'll look out of the left window, you will see Charlton Heston, part of the Statue of Liberty, and a bunch of apes.